Hi there and welcome. We are looking at Chapter 2 today, Applications of the Derivative. In our first section, we're going to be describing the graphs of functions. Now this is going to be a lot of definition work. So we're going to be looking through the definitions and we're going to be talking about what it is when we mean that we're saying certain things. First up, we have increasing functions. The definition of an increasing or decreasing function. We say that a function f of x is increasing in an interval if the graph continuously rises as x goes from left to right through the interval. That is, whenever x1 and x sub 2 are in the interval with x sub 1 being less than x sub 2, we have f of x sub 1 is less than f of x sub 2, meaning the first y value is below the second y value. We say that f of x is increasing at x equals c, provided that f of x is increasing in some open interval on the x-axis that contains the point c. We say that the function f of x is decreasing in an interval provided that the graph continuously falls as x goes from left to right through the interval. That is, whenever x1 and x sub 2 are in the interval, with x sub 1 being less than x sub 2, we have f of x1, which is the y value for x1, is greater than f of x2, which is the y value for x2. We say that f of x is decreasing at x equals c, provided that f of x is decreasing in some open interval that contains the point c. Now with that, we have two graphs. The first graph rises as we go from left to right along the graph, just rises in a little smooth, changing kind of curve. Likewise, we have another graph. We see that my function is still increasing because as we go from left to right, those y values are still increasing. Next, we're going to talk about relative maxima and minima. Relative maximum and minimum. A relative maximum point is a point at which the graph changes from increasing to decreasing. And a relative minimum point is the point at which the graph changes from decreasing to increasing. So the maximum, we can see we have a graph that goes up and then it goes down. That very most top point is a relative maximum. That doesn't mean that it's the maximum of the whole function, it just means that it is a maximum relative to those points around him. The function could continue and curve back up and go higher. Likewise, we have a function that goes down and then it goes up, and that very bottom point is a relative minimum, minimum relative to those points around him. Next, we will talk about absolute maxima and minima. Now, these are the biggest and the smallest points of the whole function that we have. So absolute maximum and minimum. The maximum value or absolute maximum value of a function is the largest value that the function assumes on its domain. The minimum value or absolute minimum value of a function is the smallest value that a function assumes on its domain. So here we have two graphs, and we have what might be considered a relative maximum here at the very beginning point, because we have a very beginning point, it goes down, then it goes up, then it goes down, decreases, and then it goes up again. So we have a maximum value. The maximum value is 5. It occurs at x equal 2. We have a minimum value of 1, and it occurs at x equal 4. In our next graph, it goes up and then down and then back up again. The absolute lowest value is that starting point at x equals 0 when y is 2. And then we have a relative maximum right here when it went up and then went down. But it is not the absolute maximum because this function's absolute maximum occurs there at the end. Now let's look at a changing slope example. We're supposed to draw the graph of a function y equals f of capital T with the stated properties. In certain professions, the average annual income has been rising at an increasing rate. Let f of t denote the average annual income at the year t for persons in one of these professions and sketch a graph that could represent f of t. So since f of t is rising at an increasing rate, that means the slope is increasing. It's not a constant slope like a line, it's an increasing slope. This means that the slope of the graph will continually increase. Here's a possible example. You can notice that the slope is continually increasing. Look at our lines here and you will notice how it continually increases on that slope. Next, we're going to discuss concavity. We say that a function f of x is concave up at x equal a if there's an open interval on the x-axis containing a, throughout which the graph of f of x lies above its tangent line, like a bowl sitting upright. F of x is a concave up at x equal a if the slope of the graph increases as we move from left to right through a f of a. Similar, we say that a function is concave down at x equal a if there's an open interval on the x-axis containing a throughout which the graph of f of x lies below its tangent line. Equivalently, f of x is concave down at x equal a if the slope of the graph decreases as we move from left to right. It's like a bowl sitting upside down is what it reminds me of. Inflection point. An inflection point is a point on the graph of a function at which the function is continuous and the graph changes from concave up to concave down or vice versa. Notice that an inflection point is not where a graph changes from an increasing to a decreasing slope, but it's where the graph changes its concavity. Notice the first depiction is a bowl sitting up and then a bowl turned over. Next one is a bowl sitting up, then a bowl turned over, and just different pieces of that bowl. Intercepts. This is a common concept that we've been discussing for a very long time. The x-intercepts are those places where the graph crosses the x-axis. The y-intercept is the point at which the graph crosses the y-axis. Asymptotes. A horizontal asymptote is a straight horizontal line that follows indefinitely as x increases without bound. Now, horizontal asymptote is going to occur when the limit as x goes to infinity of f of x, or the limit as x goes to negative infinity of f of x exists, in which case the asymptote is y equals limit as x goes to positive negative infinity of f of x. And then we have a graph showing you that I just like to think of it as what's happening at the very ends of the graph in the infinities and the tails. What's going on in the tails? Is it approaching a particular value? Vertical asymptotes, those are straight vertical lines that the graph follows indefinitely as y increases without bound. If a function is undefined at x equal a vertical asymptote occurs, in which case the denominator equals 0 and the asymptote is x equal a. These are places that the function does not exist. However, a function can cross a horizontal asymptote. It can exist at a horizontal asymptote. A 6-point graph description. When you're describing a graph, you want to talk about the intervals at which the function is increasing or decreasing, the relative maximum minimum points. You want to describe whether or not it has an absolute maximum or minimum value. Step 3, you want the intervals on which the function is concave up or concave down and those inflection points. Step 4, you want the x and y intercepts. Step 5, you want the undefined points. And step 6, you want the asymptotes. So we're going to look at this graph. This is a graph that is just a little snip of a graph. It's increasing from x equal looks like about -3 all the way up until x is -1, then it decreases when x is 3, and then it goes back to increasing when x is 3, and looks like it stops right about 5.5. So that's just a little description there. Now, number 1, they want us to describe where it is increasing and decreasing. So what we would say is that the function is increasing from negative -3 all the way up to -1 for x. And it's also increasing from 3 all the way up to 5.5. The function is decreasing from -1 to 3 for my x values. The relative maxima are at x equal -1 and x equal 5.5. The relative minima are at x equal -3 and x equal 3. Now we have a maximum, an absolute maximum value at x equal -1. That's the highest point on the function. The function has an absolute minimum at x equal -3, and that's the lowest point on the function, actually is where it starts. The function is concave up over the interval from 1 to 5.5. The function is concave down over the interval -3 to 1. Notice that the inequality symbols here, we do not include those points at which it changes. This function has exactly one inflection point, and it is located at x equal 1. That's the place where it changes from concave down to concave up. The function has 3 x-intercepts located at x equal -2.5, 1.25, and 4.5. Just guesstimating there. Don't really know for sure because it's just looking at the picture. The function has 1 y-intercept at about y equal 3.5. Could be 3.45, but just pretty close there. Over the function's domain from -3 all the way to 5.5, the function is not undefined for any value of x. Therefore, it's defined all the way through. All right. Lastly, the function does not appear to have any asymptotes, horizontal or vertical. Just knowing how to use these definitions and knowing what these definitions mean, that's kind of the goal in this section. If you need any help with any of this, be sure and send me an email. And if you have any question about homework, also send me another email. You guys have a wonderful day, and I'll talk to you later. Bye now.